Welcome back, everyone, for another deep dive. Today, we'll be exploring a rather curious corner of mathematics. Those of you who've dabbled in math probably remember factorials, right?
Yes, factorials.
You know that concept where you take a number and multiply it by all the positive whole numbers smaller than it?
Like 5 factorials, 5 times 4 times 3 times 2 times 1.
Exactly. 5 factorial, which we write as 5 with an exclamation mark equals 120. But here's the twist. We're not just interested in calculating factorials. We're going deeper. We're asking, how can we express a factorial as a product of numbers that are all relatively large?
It might seem counterintuitive at first, right? I mean, we usually think of breaking things down into smaller pieces.
Exactly, breaking them down, not building them up from larger chunks.
But that's where things get interesting. See, factorials grow so quickly. Exploring the limits of their factors gives us a new perspective on their structure.
So it's kind of like looking for the biggest possible building blocks for a factorial.
That's a great way to put it. We're trying to find the largest possible building blocks if we want to express n factorial as a product of several integers that are all at least a certain size.
Okay, now to make this a little more concrete, mathematicians have come up with a specific function. They call it TAN, and it represents the largest number such that n factorial can be written as a product of integers all greater than or equal to that number, Tn.
There's even a sequence in the online encyclopedia of integer sequences, the OEIS, it's A034258. It lists the values of Tn for small values of n.
I was looking at that sequence earlier, and it's pretty interesting. What struck me was that some numbers are missing, like 36, 49, 52, 55. You don't see them in the sequence at all. What's up with that?
It hints at some underlying structure, right? Some hidden constraints on how factorials can be decomposed.
So it's not as simple as just picking any large number and seeing if it works.
Not at all. Maybe an example would help. Let's take 6 factorial, which is 720. You can factor as 24 times 30. Those are fairly large numbers, right?
Yeah, definitely bigger than 1, at least.
But T6 isn't 24. It's actually 2. You can write 720 as 2 times 360, and all the factors there are at least 2.
So even though you can find a decomposition with larger numbers, the largest possible minimum factor is actually much smaller.
Exactly. And if you tried to use a larger minimum factor, say 3, you wouldn't be able to find a decomposition of 720 where all the factors are 3 or greater.
That's really interesting. It shows that finding this largest possible minimum factor, it's a bit more nuanced than you might initially think.
Precisely. And as n grows larger, n factorial becomes absolutely enormous.
Oh, yeah. I remember trying to calculate factorials for larger numbers back in school. They blow up really quickly.
They do. And we can get a rough estimate of how quickly they grow using something called Stirling's formula. From Stirling's formula, you can actually derive a simple upper bound for Tn.
An upper bound, meaning T at n can't be bigger than this value.
Right. It can't be bigger than the nth root of n factorial. Written mathematically, that's n factorial, raised to the power of 1 over n.
So that gives us a starting point, a sort of ceiling for how large Tn can be.
Exactly. It's a very crude boundary, though. The real challenge lies in figuring out how close Tn can actually get to this upper bound, or more interestingly, to some fraction of n itself.
So that's the real heart of the problem, understanding the relationship between Tn and n as n grows very large.
Precisely. And this leads us to some fascinating mathematical history. Back in the day, mathematicians Paul Ergens, John Selfridge, and Ernst G. Strauss made a bold conjecture.
Oh, this is going to be good. I love a good mathematical conjecture.
They conjectured that the ratio of Tn to n, this Tn over n, approaches 1 over e as n becomes very large.
1 over e, for those who don't remember, e is that special mathematical constant roughly equal to 2.718.
Right, so 1 over e is approximately 0.3679.
So their conjecture was essentially saying that even as factorials get unbelievably huge, the largest possible minimum factor Tnn maintains a certain proportional relationship with n.
That's a pretty remarkable idea when you think about it. This hidden connection between the size of a factorial and the size of its largest minimum factor.
And what's even more remarkable is that they apparently had a proof for this conjecture, but it was lost.
Ah, yes, the lost proof. It's a bit of a mathematical mystery. A real shame, because their proof likely contained valuable insights into the nature of factorials.
So for a long time, this fundamental question about the behavior of Tn remained unanswered.
Thankfully, more recent work has shed light on this problem.
Oh, really? So someone finally picked up the torch and made some progress on this lost conjecture.
Yes, mathematician Terence Tao, you might know him.
Oh, wow, Terence Tao, a Fields medalist. That's some serious mathematical firepower.
He's done some groundbreaking work in many areas of mathematics, and in this case, he made significant progress on understanding the behavior of Tn.
So what did Tao discover? Did he manage to prove the Erdos Selfridge Strauss conjecture?
He didn't prove the conjecture in its original form, but he did something even better. He established asymptotic bounds for the ratio Tn over n.
Asymptotic bounds. Can you explain what those are?
Asymptotic bounds essentially describe how a function behaves as its input grows towards infinity.
So in this case, it's telling us how the ratio of Tn to n changes as n gets larger and larger.
Exactly. And the remarkable thing is that Tao's bounds for Tn over n confirm the essence of the Erdos-Selfridge-Strauss conjecture. They tell us that this ratio does indeed approach 1 over e, but they give us much more precise information about how it approaches that value.
That's amazing. So even though the original proof was lost, the core idea of the conjecture was correct.
It was, and Tao's work gives us a much deeper understanding of why it's correct.
So tell me, what are these bounds that Tao found? How close does Tn over n get to 1 over e as n goes to infinity?
Tao proved both a lower bound and an upper bound. The lower bound says that Kn over n is greater than or equal to 1 minus big O of 1 over log n.
Okay, hold on. Let's break that down a bit. What's big O of 1 over log n?
Big O notation is a way to describe the growth rate of a function. In this case, big O of 1 over log n means that the difference between Tn over n and 1 is bounded by some constant times 1 over the natural logarithm of n.
So as n gets larger and larger, that difference shrinks at least as fast as some constant divided by log n.
Exactly. It means Tn over n gets closer and closer to 1 over e from below.
Mm.
The lower bound guarantees that you can always find factors that are a substantial fraction of n, and that fraction gets closer to 1 over e as n increases.
So the lower bound tells us we can get pretty close to 1 over e. What about the upper bound? Does it also approach 1 over e?
The upper bound is even more interesting. It says that Tn over n is less than 1 minus c naught plus little o of 1, all divided by log n.
Okay, another piece of notation to unpack. What's c naught and what's little o of 1?
C naught is a specific constant approximately equal to 0.3044. And little o of 1 represents a quantity that goes to 0 as n becomes infinitely large.
So the upper bound tells us that Tn over n also approaches 1 over e as n grows, but it does so from below.
Exactly. And the gap between Tn over n and 1 over e is not arbitrary. It's tied to this constant c naught and the logarithm of n. This gives you a much finer picture than just knowing the limiting value. It tells you something about the rate of convergence, how quickly Tn over n approaches 1 over e.
It's like having a speedometer for the convergence. It not only tells you where you're going, but also how fast you're getting there.
That's a great analogy. And this refined it. Our understanding of how Tn behaves for a very large n is a major contribution of Tao's work.
Now I'm curious about the why. Why can't Tn over n get arbitrarily close to 1 over e? What's preventing it from crossing that threshold?
The key insight lies in understanding the role of prime numbers, specifically the primes that are slightly larger than n over e.
Prime numbers always seem to sneak their way into these kinds of problems, don't they?
They do. They're the building blocks of all integers after all. Now think about this. Any way you break down n factorial into factors must include these prime factors just above n over e in one of those factors.
Because every prime number up to n is a factor of n factorial.
Right. So if a prime number p is just a little bit bigger than n over e, then any multiple of p that's at least as large as Tn will have to be at least p itself. This puts a constraint on how small the other factors in your decomposition can be.
Let me see if I understand this. Because these primes just above n over e have to be present somewhere, it forces the other factors to be not too much larger than n over e.
Precisely. They can't all be significantly larger than n over e, otherwise their products would exceed n factorial.
So it's like those primes create a bottleneck limiting how large all the factors can be simultaneously.
That's a good way to think about it. And this constant c naught in Tao's upper bound, it arises from optimizing this argument. It considers exactly how much larger the first multiple of a prime can be compared to Tn.
I'm starting to see the depth of this problem. It's not just about factorials. It's about the interplay between factorials and the distribution of prime numbers.
Exactly. And that's one of the things that makes number theory so fascinating. These unexpected connections between seemingly different concepts.
Now, you mentioned that Tao proved both a lower and an upper bound for Tn over n. We've talked about the intuition behind the upper bound. What about the lower bound? Is there a similar intuitive explanation for why it holds?
The proof for the lower bound is a bit more intricate, but I can give you a general idea. It involves constructing an initial approximate factorization of n factorial using odd numbers that are a bit smaller than n over e.
An approximate factorization. So you're not trying to get the exact factorization right
Well,
away.
not right away. The goal of this initial step is to get the size of the factors roughly in the right range.
So you're building n factorial from pieces that are about the size you're aiming for.
Exactly. But of course, the prime factorization of this initial product won't perfectly match the prime factorization of n factorial.
Because you're only using odd members.
Right. For example, this initial product won't have any prime factors larger than n over e, and the powers of 2 will be missing entirely.
So the size of the factors might be in the right ballpark, but the prime composition isn't quite right.
Precisely. And the next step is to carefully adjust this initial factorization to make it a true factorization of n factorial. This is where the prime number theorem comes in.
The prime number theorem, that famous theorem about the distribution of primes.
The prime number theorem, along with its error terms, is essential here. It allows us to match the large prime factors of our approximate factorization with the actual large prime factors of n factorial in a controlled way.
So you're essentially using the prime number theorem to fine-tune the prime composition of your factorization.
Exactly. And the powers of 2 that were missing in the initial approximation, those are used to make the final adjustments. By distributing the powers of 2 strategically among the factors, we can ensure that the final product exactly matches the prime factorization of n factorial.
It sounds like a very delicate process requiring a deep understanding of both factorials and the distribution of prime numbers.
It is. And Tao's proof masterfully combines these different areas of number theory to achieve this result.
Now, shifting gears a bit, besides these asymptotic results for a very large n, there are also some specific conjectures about the value of Tn for particular numbers.
Ah, yes. Mathematicians Richard Guy and John Selfridge proposed some intriguing conjectures. One of them states that Tn is always greater than or equal to the floor of 2n over 7 for all n, except for the specific case of n equals 56.
The floor of 2n over 7, that means you divide 2n by 7 and then round down to the nearest whole number.
Exactly. So they're suggesting a very specific lower bound for Tn. They also conjecture that Tn is strictly less than n over e for all n, except for the small values of n equals 1, 2, and 4.
So they're proposing both a lower and an upper bound for Tn. Have these conjectures been proven?
Tao's work actually addresses the upper bound conjecture directly. His proposition 2.2 in his paper proves that Tn over n is indeed less than 1 over e for all n, not equal to 1, 2, or 4.
So one half of the Guy-Selfridge conjecture is now a theorem thanks to Tao's work.
Yes. And the proof of this upper bound is quite clever. It relies on a criterion that Tao establishes in his lemma 2.1.
A criterion? What kind of criterion?
It's a condition that, if satisfied, guarantees an upper bound for Tn. It involves a sum over prime numbers p greater than the square root of t plus 1. Each term in the sum considers how many multiples of p you would need to exceed a given value t, weighted by how many times p divides n factorial.
So it's kind of measuring the density of prime factors above a certain size.
That's a good way to put it. And if this sum exceeds a certain threshold related to the logarithm of n factorial, then Tn must be less than t.
So it's like a pressure test for the prime factorization. If the primes are densely packed enough, it limits how large all the factors can be.
Exactly. And Tao cleverly applies this criterion with t set to n over e. He shows that the condition in his lemma is satisfied for all n greater than or equal to 80.
And I'm guessing the smaller values of n were handled separately.
Yes. For n between 80 and 599, the inequality was verified numerically. And for n greater than or equal to 599, Tao used the prime number theorem to prove it analytically.
It's amazing how these different tools from number theory all come together to solve this problem.
It's a beautiful example of the interconnectedness of mathematics.
Now, for our listeners out there who are eager to learn but also value their time understanding these bounds on Tn over n is a real shortcut. Instead of trying to find the absolute best way to decompose a huge factorial n-pest, you now know the fundamental limitations on how large those individual factors can be.
Exactly. These bounds provide essential insights without requiring you to go through the complexities of constructing the actual factorization.
And it's a real aha moment when you realize that even though factorials grow incredibly fast, there's a limit to how large their individual factors can be if you want a certain number of them in the product.
It reveals a hidden structure, a constraint on the multiplicative building blocks of these seemingly simple products of consecutive integers.
So in essence, our deep dive today has illuminated the significance of these bounds for t over n. Terence Tao's work has confirmed a long-held conjecture and provided a much more precise understanding of how this ratio behaves for large n. It's given us a deeper glimpse into the multiplicative world of factorials.
And while we've come a long way in our understanding, it's important to remember that the journey of mathematical exploration never truly ends.
There are always more questions to ask, more connections to discover.
Indeed. For instance, the other half of the Guy-Selfridge conjecture, the lower bound on Tn, that remains an open question for n not equal to 56.
So even with something as fundamental as factorials, there are still mysteries to unravel.
Absolutely, and that's what makes mathematics so captivating. It's a never-ending quest for knowledge and understanding.
It makes you wonder how these ideas about decomposing factorials might connect to other areas of mathematics or even other fields like computer science.
That's a great point. For example, in cryptography, the difficulty of factoring large numbers is crucial for security.
Could there be connections between the structure of factorials and the design of cryptographic algorithms?
It's certainly possible. The idea of finding the largest possible factors of a number has a similar flavor to the problems faced in cryptography.
And what about optimization problems? Problems like the knapsack problem, where you're trying to select the best combination of items subject to certain constraints.
That's an interesting connection. The knapsack problem is a classic example of combinatorial optimization. You're trying to pack a knapsack with the most valuable items without exceeding its weight limit.
So you're essentially looking for the best way to decompose a given value, the total value of the items, into smaller values subject to a constraint.
Exactly. And this idea of finding optimal decompositions under constraints has a similar ring to what we've been discussing with factorials.
It seems like there could be a lot of fruitful connections to explore between these different areas.
Indeed, and that's the beauty of mathematics. You never know where a seemingly simple question might lead you.
Well, this deep dive into the world of factorials has certainly given us a lot to think about.
It's amazing how such a seemingly elementary concept can lead to such deep and intricate mathematical questions.
Thanks for joining us on this journey. Until next time, keep exploring the fascinating world of mathematics.
And keep asking questions.
That's right, the quest for knowledge never ends.